हरिः कर्ता।
So now we will be moving on to the third section of intuitive sampling and distribution for you course. So in this we will be looking about sampling distributions made simple, a beginner's guide. Here we will be looking about various sampling distribution techniques and how can we leverage these distributions when we work with similar kind of data in data science modeling. This is very very important. Of course it's a beginner's guide, so here we won't be deep diving into the each distribution that we will be doing in inferential statistics for you course, but here we'll have a sneak peek into these respective distributions. Okay, let's begin. So, as we all know, a popular misconception holds that the era of today's big data means the end of a need for sampling. That's what people used to think, and people still they're thinking that era of big data means the end of a need for sampling. In fact, the proliferation of data of varying quality and relevance reinforces the need for sampling as a tool to work efficiently with a variety of data and to minimize bias. Even in a big data project, predictive models are typically developed and piloted with samples. That's what we did. Yes, that's what we did with our project at Volvo. So, samples are also used in tests for various sorts. Example, comparing the effect of web page designs on clicks. So, in general, data scientists need not worry about the theoretical nature of the you know your distributions left hand side, and instead should focus on the sampling procedures and the data at hand. There are some notable exceptions. Sometimes data is generated from a physical process that can be modeled. The simplest example is flipping a coin. Just flipping a coin. So flipping a coin, this follows a binomial distribution. Just for your sake of information I'm giving, but we will go through it later. So flipping a coin follows a binomial distribution. Any real life binomial situation, buy or don't buy, fraud or no fraud, click or don't click, can be modeled effectively by a coin with modified probability of landing heads, of course. So in these cases, we can gain additional insights by using our understanding of the population. So now, before we jump into our distributions, I just want to summarize whatever we have discussed before. I just want to give you quick revision on some of the terminology that we have used before. So first one is sample. A sample is a subset of data from a larger data set. Statisticians call this larger data set as the population. A population in statistics is not same thing as in biology. It is a large defined set of data. Okay. Now, so this is what a sample and population is. Now, let's move on to the random sampling. Random sampling is a process in which each available member of the population being sampled has an equal chance of being chosen for the sample at each draw. So the sample that results is called simple random sample. So sampling can be done with replacement, so in which observations are put back in the population after each draw for possible future reselection, or it can be done without a replacement, in which case observations once selected are unavailable for future draws. So both now sampling with a replacement and without a replacement, we will be looking into these things in probability, how to do now with replacement and without a replacement, probability with replacement and probability without a replacement. Okay, and so these are the key terms. So in addition to that, we have seen size of the population, capital N, and size of the sample is small n. Then we have seen stratified sampling, dividing the population into strata and randomly sampling from each strata. Then stratum or strata, a homogeneous subgroup of a population with common characteristics. Then we have seen bias, that's a systematic error. Now we will be looking into the sample bias.